Okay, so back to our class again. So this is how we create the flashing LED, yeah, and even creating the flashing is an LED pun uh, quite uh, many steps that we need to go through, right? We need to know the address of the port. We need to know the address of the direction register in order to uh, create this flashing LED application. And the program also uh, looks complicated, yeah, in assembly language. So that's why in uh, more complicated programming, we will use the high-level language, for example, C++, to program our microcontroller. And when we use this, again, we still need to configure the I/O. Yeah? This is the I/O configuration, right? But today there are many uh, what we call the library that we can straight away use in order to do the configuration like this, without knowing specifically uh, what is the address of, or what is the name of the I/O register, and also no need to access the memory by using the available library. So one from that is the ARM embed, uh, or what we call the API, application programming interface. So the ARM embed is uh, the programming interface that help the programmer to develop the application faster by using the library that is provided by the mbed. Meaning that when we use mbed, we don't need to know this, right? Where we can straight away use the available library to define where is our input, where is our output, without knowing the actual memory location of uh, the port or the pin, right? So this is the uh, microcontroller, the ARM-based microcontroller also, and this is still, this is wrong, 1768, right? So the mbed takes the microcontroller, in our case is the LBC 1768, and put a very useful support circuitry, all right, uh, and on the PCB, right? So this is the mbed layout, where this is the LPC 1768 microcontroller. So it is put on the PCB like this, and you will have the USB where you can connect to the computer to program your microcontroller, and uh, take certain, not all the pin uh, to the I/O pin here, all right? And this is the block diagram where this is our microcontroller. This microcontroller is exactly this one, right? So uh, the mbed reuse the microcontroller, and with a new connection to the external, the I/O. Also, you will have the Ethernet, the USB, and the flash memory connected to the uh, microcontroller as well to save the program. And of course, this one is for the power. So here is the mbed layout for the uh, LPC 1768 microcontroller. So the mbed, actually, if you go to the internet, right? This is a very big design environment for embedded system. So you can type embed on Google, and you can go to the website, and this is the website where you can sign up for free, right, to use this. So when we look at the hardware, there are many hardware that is embed compatible, right? Means that we can use the embed library later on. So the LBC 1768 is one of the embed compatible here. Not this one. There are many. So mbed is one of these. So we can browse to search for not sorry the LPC 1768. So we can search from here, right? So this is what we call embed embed environment. And by using mbed, we will see later on the programming, the microcontroller programming will become a lot easier as compared to what we have learned before, where we need to know very detail of the hardware. But by using the mbed, we can use straight away the library that are available uh, from the embed to configure the I/O, for example, to configure the ADC. It is a lot easier using this. It is like what you use in Arduino. That one is also another microcontroller type that use the pre-defined library in order to program the microcontroller. So this is the microcontroller that we have. It is 40 pins, and not all the digital I/O that we have here is available, right? So when we look at here, the blue color here is the pin that can be configured to digital I/O. All right, so we have P5 to P30, right? Here we can configure to as an digital I/O, and here 6 pin we can have the analog input, and we have one analog out, P18, and we have Ethernet. We have this is communication, SPI. This is UART, and this is I2C. Right? We will learn in chapter 4 the communication. PWM we will learn in this chapter, right? So how to use all the peripheral that available in this microcontroller in order to build our application, right? So this is use what is called the API, or application programming interface. So what is API? API is a software, a code, or a program sitting between the microcontroller or microprocessor and the peripheral or the hardware, right? And the user software or our program. The user software is our program. So we write the program here, and it will be interfaced with the mbed API to access the hardware of the microprocessor or microcontroller. So for example, we want to configure the I/O just like what we did here. Without using the API, what we need to know is we need to know exactly this pin is connected to what, and what is the address of this pin, right? By looking at the user manual. And to program, we need to access the correct address of this one. But by using API here, no need to know that, right? What we need to know is which one, P5 until P13, we want to configure as input. And to configure this pin as input is very easy. Later on, we will see, yeah, by using the API and the function that is available here in API. And this API will do the job for you to access the correct location or address of the microcontroller or peripheral. So the API is the interface, yeah, between the hardware and the software, right? So this part is hardware, and the API, and of course the user software is the software part. Yeah, this is the medium of communication between our program and the hardware and the microcontroller. Yeah, so the API containing the necessary codes for accessing the hardware. So the embed software development kit, or what is called the SDK, is the C or C++ microcontroller software platform rely upon tens of thousands of developers to build project fast. So this is open source SDK, means that developer around the world can provide the, uh, the library that we can use in order to build our application faster, right? And we can go to the mbed.org uh, to to use the SDK, and this is free, and this is actually online, an online uh, SDK, software development kit. So you can go to the internet, you type for mbed, and of course you can go to the website, and the website name is now is os.mbed.com. Here is the compiler that you can use, but in order to use the compiler, you need to log in, to create the account first. So here I have the account already, so I use this account. The compiler, right? Log in already. So this is the compiler that is available online, where we can write the code for our application. For example, this ADC program. So this is C++ program. Okay, and we can compile, and then we can download to the hardware, right? Where the hardware is connected to our PC. Now we can compile and straight away download our code into the actual hardware, right? So here, if you can see here, okay, so here is the microcontroller, and the size. You can you see this? Yeah, so this is the microcontroller, and you can connect your microcontroller using the USB, this USB, and connect to your computer, and you can download the code the your microcontroller. I will show you later on. So now let's look at the very simple application, just like what we did in previously, where we want to use the digital I/O. Yeah. So the first API is the digital out, where it is used to configure the control a digital output pin, where we can set a digital output. Yeah, in the previous example, we flashing the LED, right? So which means that that one is digital output. So this is the function that we will use, yeah, digital out. And this is the program that is used to flash the LED. So in the program, what we do is we need to include this header file, the mbed.h. Yeah. In the previous example, uh, we use this header lpc17xx.h. Yeah? But when we want to use mbed API, what we need to uh, use is that mbed.h, right? And to write the program, and this is how we configure the digital output. Instead of locating where is the pin in the memory address, so what we do now is to use the API, the mbed API. So the API is digital out. This is the digital out, and this is the name of the microcontroller pin in our mbed board, right? And this is the name that we give to this pin. Later on, when we use my LED or any name, so this will refer to this LED one. So what is this LED one? So this LED one is actually where is it? We have four LED, four built-in LED here. The first one is named LED 1, LED 2, LED 3, LED 4 here. So when we do this, means that we uh, want to access LED 1, and LED 1 is digital out, means that this is the output, and we give the name for this LED 1 as my LED, right? And in the main loop here, look at the main loop, while 1, same as the previous one, means that we have endless loop here, and my LED, which is this one, is equal to 1, means that this is 1. And wait function is the another mbed API. Yeah, so wait function means that we wait for 0.2 seconds. So the unit is in second here, 0.2 second, and then we off the LED, and then we wait 0.2 second, and we go back on, off, on, off again. So this wait function you can have wait in millisecond, where the uh, where the function is wait ms. If you write this, for example, you will get 1 millisecond delay, or you can have even in microsecond, 1 microsecond. So US means microsecond, but if you have wait one like this, means that you have 1 second delay. So this is API also we can use straight away. without the need to create the wait our own wait function or delay function, right? So see, we don't have any wait function here. This is internal library or the API that we can straight away use it. So the program will become a lot easier here, yeah, because we no need to access the hardware, all right? Just we need to know where is LED 1 physically, but internally we don't need to know. We don't need to know where is the address, what is the address of this pin, right? We can straight away use it. So in the program, we can write this here in the mbed. Okay, I have the program already, so let's use it. So this is program. Let's say this is not P21, but LED B1. All right, and this is 0.5 delay, so change to 0.2, 0.2. Okay, so that we have exactly the same program like this one. Okay, so I now connect if you can see here, okay, I have my microcontroller here. Yeah, this is on, yeah, connected to the to my laptop, and we will look at the LED here at the bottom here, right? When I press compile here, when I press the compile button, okay, so this is the available program in my microcontroller, actually in the flash memory. So I can save with this file name. All right, so it is program now, and I press the uh, and I will press the reset button here, and you can see that the LED is blinking now, 0.2 second. So this is the LED, the internal LED. Now let's say I connect the LED here, and the external LED. As you can see, this is external LED. I connect to the pin number 5, P5 of the microcontroller. So where is the P5? So this is P5, P5, this pin. So now my LED is connected to this pin, right? So now if I want to change the program, uh, here I just change this to P5, means that I am now make P5 as digital output, and the name is my LED. Yeah, and I compile again and see what happened. Use the same name, replace the previous file. Okay, now it is program, and let's see. Okay, if you can see that, I press reset, and now we have this LED is flashing for 0.2 interval. Okay, so you can see that by using the mbed API, now the programming is the programming now become more easier as compared to the previous method where we need to have our own configuration without using the API. But by using the API, the programming become a lot more easier. And by using the API also, we can develop more complicated program faster as compared to without using the API, right? So without using API, of course, you need to have more knowledge on the hardware, how to access all the peripheral, and where is the location and how to set to do the setting to configure all the peripheral. All right, so that's a lot more easier. And we can read the input also. So for example, if you have the switch, yeah, you can use digital in to read the input, digital input from the outside, right? And for example, now digital in and digital out is one bit, one pin at a time. Now let's, for example, if we have the application like this is the same as the what we have seen in chapter 3, where we have two switches, switch 1 and switch 2. Uh, when we switch this, when we turn on this switch, it will turn on these 4 LED, the lower 4 LED, and when we turn on this switch, it will turn on this 4 LED, and if we turn on both, it will turn on all the LED, right? So this is exactly the same with what we have done in chapter 3, right? So let's go back to chapter 3 and see here. Is it the same example here, right? Same flowchart where we have 8 LEDs, right? And we have switches, switch 1 and switch 2. Switch 1, when we press, it will turn on this. Switch 1 is this, turn on this. Switch 2 will turn on this. Yeah, exactly the same. Now we will use the mbed API to do that. So we can use the bus in and bus out. Yeah. So bus in and bus out is very good, where we can group the digital input in one group, right? Instead of using the digital in. If you use digital in, actually it can be done also, but you need to configure one by one. Yeah, digital in P5, digital in P6, for example. But if you use bus in, you can use something like this, where the input is we name it switch 1 2, yeah, is connected to P19 and P120, yeah. So for example, switch 1 is connected to P19, switch 2 is connected to P20, and LED out is connected to P28, 27, 26, 25, and 21, which is uh, 8 pins to connect to the 8 LEDs, right? And in the program, we can use case statement here. So this is the main loop. So with case statement, we can have case switch 1 2. Case 0 0 means that all are not pressed. Yeah, the switch are not pressed. So we have 0 0. The output 0 0 8-bit. So not activated. When 0 1 or 1, yeah, because this is 2, right? So 0 1. So F0 means that this one is 1 1 1 1 0 0 0 0. It will turn on 4 LEDs. When number 2 or 1 0, yeah, so 0F. And if both are pressed, which is 1 1, yeah, 1 1, 3 is 1 1. So both are pressed. So all are turned on. Yeah, FF. And other than that, so we off. Okay, so this one, 0 1 is this. This one is 0, this one is 1. Yeah, it is reverse. If 1 0 here means that this one is 1, this one is 0, right? The orientation is like that. So we can look at the output by using this. I will demonstrate using my hardware here, where I have the program. Okay, this is the program, exactly the same program in the mbed compiler, and I want to program my microcontroller here. Right, so this is a microcontroller. On the this is the electronic board where I have the visual LED. Later on I will show you what is visual LED, and visual switches. Yeah, where I can connect this board to my computer and try to demonstrate this program. So first thing is I need to program this microcontroller, where I need to connect the computer to my microcontroller here, and I need to power up this board. This is connected to my computer using the USB as well. And I need the power to power the board. So, and in my computer I need the software. So this is the software, the Waveform software, which is connected to the board, right? Because I don't have the physical switches and LEDs, so I use the software. Yeah, the I/O. So I need to do the connection a little bit here, And before that, I need to program my microcontroller first. So I just compile this code. Okay, save. And here I changed because I connect this to the switches, so I set this to be switches, right? So this is off, this is on, this is on. So and my LED is connected to, this is LED, yeah, is connected to pin 16 to 23 of this board, of my board. Oops, the connection is lost. Okay, so if I turn on this, it will turn on this all LED. If I turn off, all LED are off. If I turn on this 4 LED will be turned on. And if I turn on both, all the LED are turned on. So this number 10 is not used actually. Okay. Turn off, all are off. Turn on, all are on. So this can be configured to many things, yeah. But the hardware is not available for you, yeah. So this is for demonstration. So if you are in UTHM, then you can use it, right? So this board is very good, where it can be an oscilloscope and many other things, yeah. So it can be a scope, a waveform generator, a supply, and logic analyzer, and many more. So it is very good for application development. So that will demonstrate this program. So actually, for you, yeah, you can test your code in in on the internet. Also, you can use what is called the mbed simulator, right? So this is the simulator. For example, this program is to blink the LED, or to flash the LED. All right, so you can change the code and run the code. There are many examples here. For example, the LCD display. All right, so you can run the code, and you can have your code, and you can add the component, the LED. If you want to add LED connected to P5, you can have a new LED here, and you can run this. Right, so this is a mbed app simulator. How to use this, I will show my previous video to you. But I just found that I don't know what is the problem, whether my browser uh, or the latest version of this one is not supported by my browser. But sometimes this simulator uh, is not working in my on my laptop. Yeah, for example, if I change this to LED2 and I run the compile version, okay, it can change to LED2 flashing here instead of LED1, right? When I change to LED3, Yeah, sometimes it won't work, huh? It will hang like this. This has never happened before. And because this mbed simulator is not official mbed, it is created by the uh, advanced user using JavaScript. It is not the hardware. It is a software that simulate what is happening in the actual hardware when we have the program like this. So it's certainly has bugs in the program. So but you can try to use it. Yeah. So later on in your mini project or assignment, so you need to have the hardware, and I will recommend you where to buy the hardware in order to uh, learn this. Yeah, you need the actual hardware in order to learn this embed environment or embed microcontroller. So let's go back to this. So this is how we create the bus, or we have multiple input and multiple output, digital input, multiple digital input, and multiple digital output in our program. So we can use bus in and bus out. But if you have only a very small number of digital input and digital output, you can use the digital in and digital out. So this one is one single pin, right? Digital in what pin? P5, P6, P7 or whatever pin. Digital out P5, 6, 7 or whatever pin. Single digital input output is digital in, digital out. But if you have multiple input, multiple output, it's recommended that you use bus in or bus out. This is the logic level of the uh, microcontroller, the mbed microcontroller, and also the LPC 1768, where the logic 1 is equivalent to 3.3 volt. So anything between 2.3 volt to 3.3 volt is considered logic 1. Means that if you supply logic or voltage to the microcontroller pin, anything between this value is considered logic 1, or the microcontroller uh, identify that voltage as logic 1. Anything between 0 and 1 is considered logic 0, but anything in between 1.0 to 2.3 is undefined logic level. So please make sure that you are, when you use digital in and digital out, make sure that the logic that you feed in your microcontroller, especially digital in, when you read the voltage from the outside, so logic 0 should be below 1 volt, and the best is 0 volt, of course. And logic 1 is between this range, and the best is of course 3.3 volt or 3 volt. Okay, anything in between is not good. Undefined means that your microcontroller don't know whether that is 1 or 0. Okay, so this is digital IO, 5 to 30 of the mbed. So any pin of this you can configure to be digital input or output, right? And this is how you drive the LED. Yeah, we learned already how to connect the LED to the microcontroller. There are two ways. First is called gate output sourcing, where we connect the LED. This is from the microcontroller pin, and of course you need to have sometimes the resistor to limit the current to the LED, because sometimes the current is quite high, so it will damage your LED. So it is better to have the resistor to limit the current that flow through the LED. So if you connect like this, means that the logic is from the microcontroller, the current is from the microcontroller. Or you can have something like this where you connect the LED to the power supply here, and of course the connection is like this. This is positive, this is negative, and your microcontroller is here. And to read or to turn on your LED, you need to send logic 0 to the output. All right, if you have 0 here, means that the current will flow from here to here, then it will turn on the LED. From here, to turn on the LED, you need to send logic 1 to the output, right? Logic 1 means that this one is turned on. Here you have need to have logic 0, and then you get the LED to turn on. So normally we will use this connection, yeah, because we avoid the current to flow into our microcontroller. But these two can be used definitely. So this is how we flash the external LED. Two LED now. We have green LED and red LED. So this is the same concept where now we have two output, yeah, P5 connected to the what we call the red LED, and the P6 connected to green LED, and this is the main loop, endless loop. We turn on, turn off, uh, here LED red turn on, LED green turn off, and we wait, and we turn off the red and turn on the green. So it you can see the alternate flashing here. So maybe the last example for today. Now using any digital output pin, write a program which output a square wave by switching the output repeatedly between logic 1 and 0 using a wait function to give a frequency of 100 Hz, period of or period of 10 millisecond, right? So 100 Hz is period of 10 millisecond. View the output on an oscilloscope. Of course, you don't have oscilloscope, but I have one here. Yeah, this is my oscilloscope. Yeah, and I will show you the output later on. Measure the voltage value for logic 0 and 1. How do they relate to voltage level on page 30? So this is page 30. So we look at the voltage level later on and see whether we get this the right one or not. Does the square wave frequency agree with your program value? So this will definitely depend on our program. So to write this program is quite straightforward, where let's look at this. So we need to plan our program such that we can generate the output as required by the specification. So now we have our program, no, not program, the specification. So we want to generate the square wave. So this is our square wave. And we want this square wave to be 100 Hertz frequency. And of course, if this is 100 Hertz, the period here is 10 millisecond. So if it's 10 millisecond, means that we need to set the output to be high for 5 millisecond and to be low for another 5 millisecond. So that is the specification. And let's go to the program where we will use this as our program, and we can use the previous LED flashing program, right? Because this one is actually a square wave, but with on 0.2 second and off 0.2 second, which is 0.4 second period. Yeah, so we just need to change this program to uh, 0 to 5 millisecond. 5 millisecond. So of course this is not wait function, but wait underscore ms, means that millisecond. And we send to P5 because my oscilloscope is connected to P5. And now I do the connection. Okay, I want to program my microcontroller. Yeah, is the yeah, if you can see, here is my microcontroller, and this is the scope, yeah, connected to the scope here. And we can see the output on the screen. So I need to program this. Okay, and just save my program there, and then reset the program and look at the scope. I select the scope. So this is the output of the oscilloscope. I can start to run my scope, and here is the initial settings. So okay, I adjust the, or maybe yeah. So this is the square wave that we generate. Okay, so we can have, okay, reduce the noise. All right, stop it so that we can measure the period. So the period, we can start here until here is about 10 millisecond, right? 10 millisecond. And the output is, let's change the volt per division here. So so the output is about 2 volt. It is the magnitude is about 2 volt. So the frequency is correct, but the output, we have the voltage drop, maybe because of the LED that I have here. So maybe remove my LED. Okay, so when I remove my LED, because I have the LED, there is a voltage drop. So now I remove my LED. So let's see the output. Yes, here we have about 3.3 volt output. Yeah, the magnitude from 0 to 3.3 here. See, this is 3.3, and this is correct. Yeah, based on the specification. And we have 3.3 volt, the output. And the output is 0. This is 1 volt, 2 volt, 3 volt, and about 3 point something, 3.3. And the period is about 10 millisecond. Okay, so that is the example of this. Okay, so to do that, of course, you need the hardware. Yeah, that is why sometimes you need to be available in UTHM so that you can go to the lab and have your oscilloscope and also your microcontroller. But with limitation that we have, we need to learn online now. So what we can do is to use online tools that uh, you need to use the maybe the simulator if it's can be used, but in the project, because the simulator is now not reliable. So for the project, so you need the hardware, so you need to buy uh, the microcontroller. The cost is about 50 ringgit for microcontroller, and also other sensors, for example the analog sensors, the LED. So you can buy it online actually. So uh, uh, yeah, that is the things that you need to do, yeah, uh, to complete this course, to understand the course. Okay, so I think today we will stop here at 10:52, and we will continue next week and to see what if we have the analog input. Yeah, because most of the input for our microcontroller is in analog, right? We always heard that the world is analog. So yes, we need to read the analog input from the outside and convert it to digital representation in order to be processed by our microcontroller. So we will learn how to do that, yeah, to convert analog data, analog voltage to digital using the microcontroller, and to process that analog value in the microcontroller next week.